A sample of gas has a pressure of 200 kilopascal and a volume of 8 micrometers cubed at 100 degrees Celsius. How many gas molecules does it contain? When we start this problem, we want to list out the two equations to find out the molecules, okay? The gas molecules. So the first equation is going to be PV equals big N kBT. Pressure times volume is equal to N, big N, which is the number of individual molecules, times K sub B T. K sub B is just a constant. It stands for this. And we have another equation that is PV equals nRT. So this one is going to help you find the individual number of molecules, and this is going to be the moles, all right, of molecules. Now, moving on. It says that the sample gas has a pressure of 200 kilopascal. However, we want to convert this kilopascal into the SI unit, which is just regular Pascal. So, side note, we know that 1 kg is equal to 1 times 10 to the third g. Therefore, 200 kPa is going to be equal 200 times 10 to the third kp, the PA. All right, so this will cancel out the K. So you are left with this. Now we need to turn the volume into the standard SI unit. So we know that 1 micrometer is equal to 1 times 10 to the negative 3. No, micro means 6. Negative 6 meters. So this will be 1 times 10 to the negative 6 meters. But since it's cubed, you will have to multiply negative 6 by 3. So you have 1 times 10 to the negative 6 by 3 is negative 18 meters cubed. This is going to be your standard SI unit for that. Okay? Now, let's put these two underneath because we want to remember them. And 1 times 10 to the negative 18 meters cubed. Now you can delete this. Okay? Back to here, we want to plug in what we know. So we know that the pressure is equal to this. So we will begin finding the individual number of molecules, okay? So pressure is 200 times 10 to the third power times volume. Volume, we know that it is 1 times 10 to the, no, it would be 8 because it is 8 here. So 8 times 10 to the negative 18 meters cubed equaling to N times kBT. So kB is 1.38 times 10 to the negative 23 times T, which is 100 Celsius. But we know that, let's remove this for now. So we're working to find individual number of molecules for now, okay? So we know that 100 degrees Celsius is equal to 100 plus 273 degrees Kelvin. So it will be 373 degrees Kelvin. So here we'll have 373 as our temperature, okay, for T. Now we want to solve for big N. So you divide both sides by 1.38 times 10 to the negative 23 times 373. So 1.38 times 10 to the negative 23 times 373. You get, this cancels out. You get 200 times 10 to the third power times 8 times 10 to the negative 18 power. All that over 1.38 times 10 to the negative 23 power times 373. You get this number, which can be written as 3.1 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8. So this is the number of individual molecules. So I'm going to write it right here. Okay, now moving on, we want to find the number of moles of molecules. So remove this. PV is going to equal to little n, which stands for moles, times R times T. So PV, we know that it is 200 times 10 to the third power multiplied by 8 times 10 to the negative 18 power, equaling to N, which is the number of moles, times R, which says right here that it's 8.3, times T, which is here 373. Now we want to divide 8.3 times 373 on both sides to solve for little n. So this cancels out, and then you're left with 200 times 10 to the third power multiplied by 8 times 10 to the negative 18 power, all that over 8.3 times 373. You get a 5.16 yada 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 times 10 to the negative 16. So n is going to be equal to around, let's say, 5.2. Let's round it, times 10 to the 16. So this little n is going to be equal to 5.2 times 10 to the negative 16. This should be a negative 16. And there you have it. You have the amount of individual molecules that this sample of gas contained and the number of moles of molecules that this gas contained.